I will begin. I think I have a scripture to start class with here. So this is Proverbs 18:2. A fool does not delight in understanding, but only in revealing his own mind. So that's how I feel sometimes. Anyway, I will begin with a word of prayer. Dear Father, we thank you for this day, and thank you again for these students, this class, and your creation. Help us to understand a little bit more about calculus today, Lord. In your name I pray, Lord Jesus. Amen. So we are in the midst of studying minimums and maximums and how to graph with calculus and all that. So last time I defined local minimum, local maximum, global maximum, right? And I gave examples. We learned that there's something called a critical point. And a critical point is a place where, thank you, either the derivative doesn't exist or the derivative is zero. And we've seen that just because you've got a critical point in your graph, it doesn't mean that you've got a local maximum or minimum. It could be like a saddle point. It could be like a vertical tangent. We saw that for the x cubed and the cube root function last time. So if you missed that class, you really should watch that. Now, that brings us to Fermat's theorem, which I'll start class with here. So this is Fermat's theorem. And Fermat's theorem says this. It says if f has local extreme value of f of c, then and f prime of c exists, then f prime of c is equal to 0. Right? So let me go through the proof here. Here is the proof. So suppose it is a local, suppose f of c is local max. All right. What that means then is then there exists a delta, let's say delta 1 greater than 0, such that f of c plus h is what? It's less than or equal to f of c, right? For all h in the ball of radius delta 1 centered at c. All right. Oh, my bad. Centered at 0 there, I should say. Let's see here. Let me just kind of draw a picture to show you what I'm doing here. So here's the graph. Here's C. Right? And to say that it's a local maximum of f of c means that I can pick some delta, right? So that if I'm, like this, so that would be like, that right there would be the c minus delta to c plus delta, right? So you could think of h as being kind of a variable that ranges between plus or minus delta, and that will take you to kind of like this part of the graph, right? So for local there, we have that the value of the function is greater than, values of the function are greater than f of c. All right. Furthermore, since f prime of c exists, so what does that mean? that means that the limit as h goes to 0 of f of x plus h minus f of x. Oh, my bad. I think I should have a c there. Yeah, sorry. Is equal to f prime of c, right? And that's a real number. Now, if h is greater than 0, then what do we have? Then we can say that f of c plus h minus f of c divided by h is greater than 0, or equal to 0, I suppose. How do I get that? How does that logically follow from what I have above? Do you guys understand what I'm doing? It's not really that much. What I'm saying is you can take this inequality right here, right? And you can subtract, wait a minute. Oh yeah, I'm a dummy. So subtract f of c. I've got, this is what's wrong. That was supposed to be what? I was about to say, I can't get that. Well, the reason I can't get that is because it's not what I'm supposed to get. If I subtract f of c to the other side, I get f of c plus h minus f of c is less than or equal to 0, right? So if I divide that by h, it's still true because h is a positive quantity. It doesn't mess up the inequality. So I get that. Right? Hence, the limit as h goes to 0 from the right of f of c plus h minus f of c divided by h is less than or equal to the limit as h goes to 0 from the right of 0, which of course is equal to 0. But I should also say that this is equal to what? F prime of c, right? F prime of c has to be equal to the left and to the right limits. But then by the squeeze theorem, I have that this is less than or equal to that. So that gives me f prime of c equals to 0. Well, excuse me. This just tells me what? My bad. It doesn't tell us f prime of c equals 0 yet. We just get f prime of c is what? Less than or equal to 0. See that? Because we've got f prime of c is equal to this, but it's less than or equal to that. Right? On the other hand, if h is less than 0, what do you get? Then we have f of c plus h minus f of c. What happens when you divide that non-negative quantity by h? If h is less than 0, when we divide, we do what? Here we preserve the inequality. Now we flip it, right? To be clear, I'm just using this over here as equivalent to f of c plus h minus. I wish I'd written that out. My bad. It would have been good for me to write this explicitly earlier in the proof because I'm using that. Okay, that is what we have since f of c is a local maximum. So since that is less than or equal to 0, when I divide by a negative quantity, I flip it over, and thus I get f prime of c is the limit as h goes to 0 from the left of f of c plus h minus f of c divided by h is greater than or equal to the limit as h goes to 0 from the left of 0, which is equal to 0, which tells me that f prime of c is less than or equal to 0. So what happens then? If you've got f prime of c is less than or equal to 0, and you've got f prime of c is greater than or equal to 0, what does this tell us? Yeah?
F prime
Right.
Also, you mentioned you wrote F times C is less than or equal to 0.
Oh no, I did. I did read the verse at the start, right? So let's see here. So there you go. Yes, thank you. Yeah, inequalities are hard, you know? It's really easy to flip them, unfortunately. And they mean totally different things. Equality is far more forgiving, isn't it? But there you go. This is Fermat's theorem. So what this gives us is a blueprint for finding local extrema, right? Okay, so fine. This is only half the proof. What's the other half of the proof? If it's a local extreme, it's either a min or a max, right? This is the proof for max. But if you can do this, it's pretty easy to see that the minimum, if it's a local minimum, instead of having less than or equal to, you have greater than or equal to here. And basically the blue and the red arguments just flip-flop. But it's the same thing. Argumentative, like in terms of the symmetry, the argument's the same. All right, so let us go on here. The next thing we have is Rolle's theorem. But Fermat's theorem is always in the backdrop. Like Fermat's theorem guides us. It guides us. It tells us that, you know, if we're looking for a minimum or maximum, then we need to look for where the derivative is 0 or undefined, because we can rest assured that that's where it's going to have a minimum or a maximum. Here's what Rolle's theorem says. Rolle's theorem says suppose you've got a function such that number one, f is continuous on the closed interval a to b. Number two, f is differentiable on the open interval a to b. So what's the difference between closed and open intervals here, guys? Yeah, the closed ones include the endpoints, whereas the open one does not. All right. Item number 3 here, f of a is equal to f of b. All right. Then, here's the punchline. There exists C in the open interval from a to b such that f prime of c is equal to 0. This is Rolle's theorem. Uh-oh. That's not good. I don't have the proof written in my notes. We'll see what happens. I'll try. All right. Okay, so I thought I had the proof here. Anyway, usually what I talk about when I'm talking about Rolle's theorem is just a little bit about, like, what is it, how to understand it. It's very natural if you think about the relation between, say, derivatives and motion. So if we think about, say, f being equal to y and x being equal to time, right? Then what's the derivative? What's dy dt? It's the velocity vertically, right? If we think of f is equal to the y, if we think of f equals to y, so interpretation, if we think f of t equals to y and t equals to time, then what's df dt equals to? Well, it's dy dt, right? Which is the what? So-called vertical velocity. So Rolle's theorem then says if you have something, right, and at time A, it's at one position, right, and at time B, it's again at that position, then there has to be a time in between time A and time B where the velocity of the marker was 0. In other words, Rolle's theorem really just says what comes up must come down, if you want to think of it physically. If you wanted to draw a graph, it's very natural as well. So you've got A, you've got B, right? You've got a continuous function from A to B. So it's got to do, I don't know what it does, but it could do all kinds of crazy nonsense. But it's got to be differentiable, right? So there has to be a point between A and B where you have a horizontal tangent if this is the situation, right? Do you guys see that? See, like here, so like this would be a potential C, or this would be a potential C, or that would be a potential C for my Rolle's theorem. So like there could be more than one C which gives you zero velocity, zero derivative, right? But there has to be at least one. Can you guys see, what if we were not differentiable on AB? Can you think of an example where Rolle's theorem wouldn't work before I prove it? Like what's an example of a function which is continuous but not differentiable? How about like absolute value, right? If I started here and started back there, this function, right? If this has slope, say -1, and this has slope 1, right? And suppose that that point is whatever, x0, let's say. Is there any point with zero slope? I mean, I'm saying it starts and ends at f of a equals f of b, right? But it doesn't satisfy Rolle's theorem because Rolle's theorem doesn't apply, right? This function has not met the terms and conditions for Rolle's theorem because the derivative at x0 does not exist. Consequently, Rolle's theorem doesn't apply. So there's no contradiction here. It's just this is like out of bounds for the theorem, right? Okay, so my proof, I have a hint. If f is a constant function, right? So you guys are going to have to help me out with the proof here. If f is a constant function, then f of x is just equal to c for all x in a to b, right? So then, of course, f prime of x is what? Is equal to 0, 0 for all x in a to b. So, yeah. So, Rolle's theorem is true. In the case that the function was constant, we trivially satisfy this. I mean, it's the best of all possible scenarios, right? Every single stupid point between a and b gives you a critical point, right? Another way of saying Rolle's theorem is that if the f of a is equal to f of b, and the function's differentiable between a and b, there exists a critical point, right? There exists a place with derivative 0. All right, so then what? If f of x is, either f is what? F of x is either what? It's either constant or it's not, right? So else f of x is not constant on a to b, right? So what do you think our next move would be here? Do. Just a second here, I would find something. Ah. So my computer's let me down. I will eventually find it. See, there are two ways we could go here. I could just try to prove it and see what happens, but I don't want to waste 20 minutes your day. So I think it's probably in our best interest for me to find my notes. I think I found them. All right, found. Let's see here. Well, getting there. Wrong chapter. Here we go. So the hint in my notes is useful, of course, but all right. All right, so thus there exists x naught in AB such that what? F of x naught is what? Well, you could say a lot of different things, but it's not equal to, for the sake of picking on something, we're going to pick on A. All right, f of x naught is not equal to f of A. All right? Does that make sense? If it's not constant, there has to be some point where it doesn't, the value of the function does not match the value of the function at A, right? What are the two cases then? So either you have f of x naught is less than f of A, right? Or you have f of x naught is greater than f of A, right? All right, so then what? So what I say then is, then if, say my eyes don't work. Goodness gracious. Ah! Stupid double scrolling got me. So I say then f of A is not the absolute maximum. So if x naught is an element of AB and f of x naught is greater than A, then f of A is not the absolute maximum. Let's see here. This implies f of A not absolute maximum. Does that make sense? Of f on AB. So we're using the extreme value theorem. Remember the extreme value theorem said that if f is continuous on the closed interval, it attains its minimum, its like absolute minimum and maximum. Remember that? So if f of x naught is greater than A, then f of A is not the absolute maximum of f on AB. So then what? So we deduce that C, an element of AB, is the absolute maximum. All right. Which implies that there exists C, an element of AB, such that f of C is absolute maximum of f on AB. And then how does that help us? Sorry I'm going so slow. I'm just kind of dumb this time of the morning. So then what? Fermat's theorem, right? If it's the absolute maximum, it's also a local maximum. Therefore, since the derivative, well, how do we know the derivative exists? Because we assumed it exists, right? It's differentiable on AB. So what's this tell us about C? F prime of C is 0. Which is what we were trying to prove, right? That there exists a C on A to B such as 0. Now, on the other hand, a very similar argument in the other case will work, right? If f of x naught is less than f of a, that means what? F of a is not the what? It's not the absolute minimum, which then means by the extreme value theorem, something else has to be, right? But wherever that happens, it has to be a critical number. That's the rest of the proof. And it's almost the picture we drew already. Yep.
Could you use the derivative function of f and just use intermediate value theorem?
Is there a proof by the intermediate value theorem for the derivative function?
Because there are only two possibilities.
But I don't know that the derivative function is continuous. So I can't apply the intermediate value theorem to the derivative function itself. But that's a good idea. Maybe if we knew the continuity of the derivative function, we could do that though. But I'm not assuming that. I'm just assuming differentiable, but not necessarily continuously differentiable. But I should think more about what you said after class. Let's see here. So moving on, if I can move on, what's up next? Well, all right. So Rolle's theorem is not, Rolle's theorem is interesting, but it's not really the main event. The thing that is most important to us, and the thing that's really the bedrock of our later analysis, is what's called the mean value theorem. All right? And the mean value theorem is as follows. All right, so here we go. So that's like the mean in the sense of, statistics, median, mean. So mean really just means average. You could call it the average value theorem. You wouldn't be wrong. You'd just be in a minority. Oh well, I tried. So it says the following. Suppose f is function such that number one, f continuous on the closed interval a to b. Number two, f differentiable on the open interval a to b. Then there exists C in the open interval from A to B such that f of B, let me write it down here, f of B minus f of A over B minus A is equal to f prime of C, aka f of B minus f of A is equal to f prime of C times B minus A. If you prefer, you could write it that way. This is the mean value theorem. Now, you can also apply this to gain an intuition for what it's saying to like a problem of physical motion. For example, if when I'm driving home, suppose my house is 10 miles from here, right? And suppose that I manage to travel there in 5 minutes. what would that mean? If I travel to my house 10 miles away in 5 minutes, what would my average speed have been? 60 miles an hour is a mile a minute. So if I go 2 miles a minute, how fast am I going? 120 miles an hour. See, so if I could somehow travel home, suppose I had a helicopter, from here to my home, 10 miles from here, in 5 minutes, then my average speed would be 120 miles per hour. The mean value theorem says there's some point in that journey, right, between where I start here and between when I get home, where the instantaneous velocity is 120, right? Or if you like a more realistic example, to get my home 10 miles from here, it takes me about 20 minutes. So that means that my average velocity was 30 miles per hour. So that at some point in my travel home, I had to be going 30 miles an hour. That's what the mean value theorem tells me. The proof of the mean value theorem is actually much easier. I don't tend to test the proof of Rolle's theorem or Fermat's theorem because they're really kind of fussy inequality arguments, which are easy to get confused about if you're not really solid on inequalities, and if you're just a little bit tired. But the proof of the mean value theorem is actually really, really beautiful and not that hard to understand. And so it essentially boils down to making use of what's called the secant line. So if I've got a graph, right, from A to B like this, suppose this is my function y equals f of x, right? I can make a secant line from A to B. And how would I do that? Like, what's the formula for the secant line which begins at A and goes to B? So that would be the secant line. Y equals s of x, the secant line of x. So the formula for that is just this. F of b plus f of b minus f of a divided by b minus a, parentheses, times x minus a. See, that gives you, by the 2-point formula for a line that begins at f of a, right, and goes to f of b when x is equal to, oh, my bad. I'm supposed to put hold on a second. There's two different choices here. I may have chose badly. Oh yeah, my bad. I was supposed to put, if I put an a here, I should put a here. My bad. A, yeah. You could either base the 2-point formula at the point a comma f of a or at the point b comma f of b, right? So I'm using a comma f of a for like the base point of my secant formula. All right, great. Now what? Now the trick is to use that to construct a new function. We're going to call it h of x. So let h of x equal to the function, I think, minus the secant function. I'm trying to follow my notes exactly. I have a very bad memory. Yeah, function minus the secant function. So then what? What's that give us? The formula explicitly is f of x minus f of a minus f of b minus f of a divided by b minus a times x minus a. Now think about this. Because f of x and s of x begin and end at the same point, what does that make h of a equal to and h of b equal to? Observe. H of a is equal to what? F of a minus f of a, which is 0. And h of b is what? It's also equal to 0. You plug it in right here. See it? See how that goes? When you plug b in, you get a b minus a, and you get a b minus a, they be canceling, and you get f of b minus f of a minus f of b minus f of a, which gives you 0. It's manifest, though, from the picture that f of x minus s of x is equal to 0 because they're joined at the, they have coterminal beginning and ending points, right? They start and end at the same point. Great. How about this? Is h continuous on the closed interval? Can you tell me why h is continuous? Given the assumptions of the mean value theorem? F is continuous, right? And what is this? What's this? This is the formula of what? It's the formula of a line. Is a line continuous? Yeah, we know a line is continuous, right? Is a line differentiable? Certainly is, right? Is F differentiable? By assumption it is. Therefore, H is continuous and it's differentiable on the open interval. What does that mean? Hence, H prime of x, which is equal to what, by the way? H prime of x is literally equal to F prime of x minus F of B minus F of A over B minus A. Do you guys see that? When I differentiate the formula for H, I get the derivative of F minus the slope of the secant line, which is namely F of B minus F of A over B minus A, right? And by fill in the blank theorem, there exists C in AB such that what? H prime of C is equal to 0, which gives us that F prime of C is equal to F of B minus F of A over B minus A, which is of course what we're trying to prove. Can you guys fill in the blank? What theorem do we need to use here? Somebody must know. You got basically three choices. You got Fermat's theorem. You got the extreme value theorem. We talked about that one, right? Or you got Rolle's theorem. Which one is it? I have a vote for option number 3. That would be correct. Rolle's theorem is the one. See, because we have satisfied the condition for Rolle's theorem. H of A is equal to H of B, right? And because they're equal to 0, both. It's continuous, it's differentiable, therefore there exists a point which gives us derivative 0 for the difference of the function in the secant line, which is tantamount to saying that there exists a C such that the instantaneous rate of change for the function is equal to the average rate of change for the function, which is the mean value theorem. All right. A lot of proofs on one day, I know. Let's see if we can do an example here. If I have time. Oh, I've got time. So the usual homework problems that you run into with respect to these directly is you might run into a problem which says verify Rolle's theorem or verify Stokes' theorem. What would that mean? What does it mean to verify a theorem? What that means is you take the function you're given and you check that it actually satisfies the terms and conditions of the theorem and shows the theorem in that particular case to be true. That's a verification of the theorem, right? In some sense, it's like finding anecdotal evidence for the theorem being true, right? It doesn't prove the theorem, but it might help you understand the theorem better. So I'm sure I have problems like that in the homework, at least one of which I'll collect. Let's see here. I do need to tell you guys which ones I'm collecting. I haven't done that yet, but I'll get around to it. Okay, so how about this? Example 1. Suppose we have f of x equals to x squared plus 3x minus 7. And let's look at it on oh, I don't know, 1, 2, 3. You know, verify the mean value theorem. Right? So what do we have to do for that? Let's work it out. So f is continuous and f is differentiable where? Everywhere, right? It's a polynomial. So certainly MVT applies. Right? If it's continuous on the real line, and if differentiable on the real line, it's certainly continuous and differentiable on the closed interval from 1 to 3 and the open interval from 1 to 3 respect. You know? So what's f of 1? What's f of 3? Can you guys tell me? 1 plus 3 minus 7 and 9. Well, 3 squared, right? 3 squared plus 3 times 3 minus 7. What do we got? Negative 3. F of 3 is 11. Oh, okay, cool. So f of 3 minus f of 1 over 3 minus 1 is equal to what? It's equal to 11 minus a minus 3 divided by 3 minus 1, which is what? Looks like 14 over 2. So that's 7. So the question is, that's equal to f prime of c for what c? For what c is that true? See, if we can find that c, that verifies the mean value theorem for this function on the interval 1 to 3. So how do we find f? How do we actually find the c? Does the mean value theorem tell you how to find it? Certainly doesn't, right? But how do you find it? How about we just differentiate and work it out, right? So what is f prime of x? We got what, 2x plus 3, right? And so we want to solve that is equal to 7. That gives us what? 2x equals to 4. So x equals to 2. So f prime of 2 is equal to 7. So in other words, we can put c equals to 2, and that verifies the mean value theorem. Does that make sense? So that's what's meant by verify. Same for Rolle's theorems. Like for Rolle's theorem, you need to verify that the values of the function match at the beginning and the ending of the AB, and then find the place where the derivative is 0. Yep.
Just one question about Rolle's theorem.
Uh-oh.
Could you extend that so that the f dx, I mean, yeah. Yeah.
dA?
Not sure. The derivative of f prime of a is equal to f prime of b.
Uh-huh.
And so then, therefore, there is some point between a and b such that f of that point is equal to.
Oh, again, I think you need the I think you need the continuity of the derivative to do what you're thinking about. If I'm wrong, if I'm not wrong. But we can talk more after class about that. So, any other questions about these theorems looking at here, guys? So, let me tell you where we're going. So the next thing we're going to do is we're going to explain how the mean value theorem immediately makes a connection between the sign of the derivative, like plus or minus, and the function being increasing or decreasing. What does it mean for a function to be increasing? It means that if a is less than b, then f of a is less than f of b. A function is decreasing if a is less than b implies f of a is greater than f of b. So increasing functions preserve inequalities, decreasing functions reverse inequalities, right? That's, and I'm at the moment I'm talking about strict increase and strict decrease. Technically, increasing is like less than or equal to. And anyway, so next time we'll talk about the careful definition. Excuse me. Oh no, that's not a good sign for the rest of the day. Oh wait a minute, I'm not teaching, I'm just giving a test. It's not you guys, it's safe. It's safe. So getting to my point, so we will soon talk about increase and decrease of functions and talk about how the derivative being positive or negative will tell us what the situation is. That will straight away lead us to the first derivative test, and then we'll also discover the second derivative test. We'll talk about concavity, and before you know it, we'll have a full set of tools to graph functions with calculus. So my apology for the density of proofs today. It should decrease as we go on here.